Okay, and on to part one here of this Pure 3 video, which is on complex numbers, so definitely one of the more difficult topics on the Pure 3 paper. So let's get started. There are two main different kinds of questions. This is certainly one of them. So we're given a complex number here defined by u is equal to 3 plus 2i over a minus 5i, where a is a real number, not complex, and express u in the Cartesian form x plus ioi, where x and y are in terms of a. So notice we're not looking for x being 3 or something, we're looking in terms of this constant a. Now, as soon as I see a complex number like this, so 3 plus 2i over a minus 5i, so some kind of quotient, some kind of fraction, I want to multiply by its complex conjugate. If you go back to surds a long time ago, we used to do this for rationalizing denominator. It works exactly the same way here. So I want to multiply top and bottom here by a plus 5i, so it's kind of evil twin here. And the reason we're going to do this, which will come clear as we go through the working, is that we actually get the bottom as a real number. And you'll see why that's useful a bit later on. So essentially here we need to multiply with FOIL. Again, we're having to work with I, so we need to be a little bit more careful. So if we do the top here, 3 times a is equal to 3a, 3 times 5i is 15i, 2i times a is 2ai. Try and get alphabetical order, makes your life a lot easier. And then 5i times 2i is going to be 10i squared, which we'll simplify in a moment. Now if we do the bottom part here, a times a is a squared, a times 5i is plus 5ai, minus 5i times a is minus 5ai, so notice they're going to cancel a bit later, and then minus 5i times plus 5i is minus 25i squared. We can do a bit of simplifying because remember that important fact that I is just equal to the root of minus 1, which means anything with I squared in is going to be just equal to minus 1. So notice we have an I squared here, that's just a minus 1, so this is going to become minus 10. So we get 3a minus 10, so that's the real parts done here. And then we've got the I parts here, so we've got plus brackets 15 plus 2a. So notice I'm putting the coefficients here, the 15 and the 2a together, and factorizing out the I. If we do the same at the bottom, notice minus 25i squared, that's going to become a plus 25, so we get a squared plus 25, and notice here these two things cancel, so we do get the whole number at the bottom. At this point, we can tidy this up slightly. So what I'm going to do is separate this out. So we get 3a minus 10 over a squared plus 25. And then we get plus 15 plus 2a over a squared plus 25i, so that we can get it in the form of that x plus yi that we're looking for. So to make it really clear to the examiner, x is equal to 3a minus 10 over a squared plus 25, and then the y component here is equal to 15 plus 2a over a squared plus 25. So again, make it very clear to get those marks, those 3 marks here, which could be crucial marks in making sure that you get a good grade on Pure 3. Now on to part B, they do like a little bit of a twist here. So given that the argument of this complex number is equal to pi over 4, or quarter pi, find the value of a. Well, let's think of the complex number here if it has the argument of pi over 4. Now remember, that's just equal to 45 degrees in 0 degrees, and notice that's just going to be this angle here if we do a complex number. And because this is pi over 4, if I was to draw in this triangle, well, this also has to be pi over 4 because we've got a right angle triangle, and this is essentially isosceles, and that means that these two sides have to be the same. So what I mean by that is if this is 2, for example, in the real plane, then this is going to be 2i. So it's going to be 1 plus I, 2 plus 2i, 3 plus 3i. These coefficients are always going to be the same. Now, how does that help us with the question? Well, that basically means that this x component and the y component have to be the same number. So what that means is that 3a minus 10, I've got my notes over here, over a squared plus 25 is equal to 2a plus 15 over a squared plus 25. If it was pi over 6, pi over 3, that would change things ever so slightly. We'd have to actually work out the ratio in which the sides work, but here they're just exactly the same. Now this looks like a kind of ugly equation to solve. We might get cubics or quartics coming out of this, but actually it's not as bad as it looks. We cross multiply, which is a standard process with algebraic fractions, so we get brackets 3a minus 10 brackets a squared plus 25 is equal to 2a plus 15 times a squared plus 25. Notice we have a squared plus 25 on both sides, so we can just cancel through. And now we go right back to iGCSE easy maths with a nice equation to solve here. Again, you've done lots of this, and then we should get a here as 25 for our answer. Notice find the value of a is only one answer here. It's always a thing I would double check, and it's a 2-mark question, so there shouldn't be too much work involved. Again, you can have a look through the mark scheme to see how we got to the answer and where you pick up those method marks. Now, the second kind of question that appears quite a lot is working with the loci of complex numbers on the Pure 3 course. And that means you need to know these 3 formulae, essentially off by heart. So when we actually start drawing these complex numbers, we can then work out if we're drawing a circle, when it's in this particular form, a so-called half line, you're going to see an example of this in this video, and a perpendicular bisector if it's written in this particular form. You're going to have to learn these off by heart and then know when to apply them depending on the question. So let's get straight into an Argand diagram star question. So we need to shade the region whose points represent complex numbers z satisfying these particular inequalities. Now, to help you understand this, what I then tend to do is I have one diagram where I'm working in the real and imaginary plane, and then I have one which is working with kind of standard coordinate geometry, and you can see the parallels between that. So first of all, we want to start with this one over here. Z minus 2i is less than or equal to z plus 2 minus i. So if we go back to our list here, what does that look like? Well, that looks like number 3 here when it's in this form. So I just like to write this nice and carefully here. So we've got z minus brackets 2i, so we're nice and clear. And again, I'm going to work with equals, and we'll talk about the less than or equal sign later. And then we have z minus, so we want it in the right form here, and that's going to give us then I minus 2 or minus 2 plus I. So I'm just writing exactly the same form as you see here with number 3. So what does this actually mean? So if I draw my real and real imaginary plane here, so real and imaginary. So we have essentially here 2i to work with. So let's pop that on here. So that's going to be 2i. And then we have minus 2 plus i. So minus 2 plus i, that's going to be here. So this is minus 2. This is single I. And this is where we come across. I'll rub that out because we're going to need space later on. And what we want to do here is find the perpendicular bisector between these 2 points. Now, if I was to go back to iGCSE standard and just draw this on a normal plane with x and y, this is essentially equivalent to me having the point here 0, 2, and me having the point over here of minus 2, positive 1. And I want to find the perpendicular bisector that goes through them. So, quick reminder of how to work out perpendicular bisector. First of all, we need the midpoint, so we need halfway in between them. So that's going to give us minus 1 and 1.5. That's useful later on. Then we want to find the gradient of the line in between them. So remember your rise over run, so y2 minus y1 over x2 minus x1. Again, it's all a reminder of iGCSE stuff you've done before. So we get 2 minus 1 over 0 minus minus 2. And that's going to give us a half. Therefore, the gradient of the let's just call this not perpetrator, but perpendicular. Well, that's going to be negative reciprocal, so flipped and change the sign. So we get minus 2. And this looks like minus 2, so that looks good. So we get y equals minus 2x plus c. We now substitute in the midpoint. So we substitute in 1.5 minus 2 brackets minus 1 plus c. Again, this is all quick reminder for you. And then 2 plus c. And that gives us then c is equal to negative 0.5. So if I draw in my perpendicular bisector, It's going to go through here, like so, and it's going to cross this point at minus 0.5. Notice working in the complex plane here, so we're going to get a minus 0.5i like so. We could also work out this point as well by just taking our solution over here and making this equal to 0, so we could also do that to work out this, okay, which is probably quite a useful thing to do. So let's work this out. So we've got 2x is equal to minus 0.5, so x is equal to minus 0.25, okay, so that's on the real axis, so minus 0.25. Okay, so we've done the first part here. Again, we're going to deal with the less than or equal to a bit later, but we've now got this written in. Now we have our second part here. So the argument of z plus 1 is less than or equal to pi over 4. Okay, so if we go back to what we've seen here, again, what form is this in? Well, this is in form of number 2, a so-called half line. Again, we'll talk about that in a moment. Again, argument of z minus z1 is equal to alpha. Okay, so if we write this in the right form here, so we've got z minus, remember there's a minus here, so we're actually going to start at minus 1. This is why I go through this. And the way that we draw this half line, so let's do this in black here. We're going to start at minus 1. So notice it's going to be further over here. So that's important for our diagram to make it accurate. And we're at pi over 4, which means we're just going to go one along and one up because we've got a 45-degree angle. So we get a line that looks something like this. This is called a half line because we stop at this point. We don't actually go any further here. And we have an angle of pi over 4. So now we've got our diagram here. The last part that we need to do essentially, and we go through I here by the way, is work out which part we want to shade in. So you want z minus 2i is less than z plus 2 minus I. So essentially we are going to go in this, so we've got a perpendicular bisector here. We're going to go this direction. And then we've got this being less than pi over 4, so we want downwards from here, which means then, this is like the inequalities you do at iGCSE, so we're going to shade in this part here to give us then all 4 marks for this question. Again, just like with linear programming or inequalities you did before, we have to consider what effect this has less than in order to work out which part we want to shade in. So, I'll show you the solution here. Notice we need this part in here as well. And it should be going through 1i. Again, strictly speaking, they should be using the real imaginary plane here, so it should be 3i, 2i, 1i. But again, this is perfectly fine. And then we shade in this particular part here. So these are the 2 main kind of questions you need to be aware of on the complex numbers in order to succeed in the Pure 3 exam. Right, let's look at another style of question here. If you're liking this video and this is really useful to you so far, then please do like and subscribe. And hopefully I'll be creating more Pure 3 content. Maybe I can create a complex number video that's a bit longer and goes through a lot of these different kind of questions rather than keeping it to 20 or 25 minutes. Right, so we've got question 8 here, and it's given, again, we've got this quotient of a complex number is equal to lambda 2 minus I, where a and lambda are real constants. And from this random information, we need to then generate this quadratic. Okay, so the first thing I'm going to do here, so we've got 2 plus 3ai over a plus 2i is equal to some lambda 2 minus I. So the first thing I'm going to do is multiply out this bracket and bring this over. So that gives us then 2 plus 3ai. Let's multiply this out, so we get 2 lambda minus lambda I, and then bring over the a plus 2i. Again, 4-mark question, there's going to be a bit of working involved. Then what we're going to do is just expand out the bracket. So let's see if we get everything together. Again, keep it in alphabetical order. So we have 2a lambda, so where lots of lambdas and i's go in different places, plus 4 lambda I minus a lambda I, and then we've got minus 2 lambda I squared. Okay, and now we just continue. Again, just take it nice and calmly. Remember, I squared, as talked about in the previous question, is equal to minus 1. So it's going to be a plus 2 lambda. So that means we bring the real parts together, we get 2a lambda plus 2 lambda here. And then for the imaginary component, we get 4 lambda minus a lambda I. Now, the reason we structured it in this way is we want to compare a real and imaginary parts together here. So let's get my highlighter. And notice this 2 is going to have to be equal to whatever this real part is over here, which means then, let's get the pen out instead, that then 2a lambda plus 2 lambda is equal to 2. Okay, this is fairly straightforward to deal with. We can cancel through by 2, so we get a lambda plus lambda is equal to 1. Factorize out the lambda, gives us this, and that means then that lambda is equal to 1 over a plus 1. Okay, that's going to be useful a bit later on. Now we've got the other component. Let's get a slightly different highlighter. Let's go with light blue. So this means that this part, the 3a, the bit in front of the I, is equal to this part here. So let's write that out with the red pen. So that means that 3a is equal to 4 lambda minus a lambda. Now we know what lambda is equal to, 1 over a plus 1, so we can pop that in. So 3a equals 4 over a plus 1 minus a over a plus 1. So we're getting towards this quadratic. Let me give myself a little bit of space. There we are. So let's create a new slide, because we're probably going to need more space on this. So 3a equals 4 over a plus 1 minus a over a plus 1. So then we can just times through by a plus 1. So we get 3a brackets a plus 1 is equal to 4 minus a. And if we do a bit of expansion here, so we have 3a squared. Maybe I don't need room after all. 3a squared plus 3a is equal to 4 minus a. And we can tidy this up. Let me just write it on a new slide. 3a squared plus 3a is equal to 4 minus a. And then bring everything to one side. So we get 3a squared plus 4a minus 4 is equal to 0. And notice always a great feeling in these questions, with the show that questions, that you do get to the quadratic that we were looking for. So that's a great feeling to have. From there, we need to find, so even if you didn't get part A right, again, you can use that now in part B, which is find the possible values of A and the corresponding values of lambda. So it's quite a nice 3-mark question here. So our quadratic was 3a squared plus 4a minus 4 is equal to 0. And now, particularly at this standard, A-level standard pure 3, I like a quick way of doing this. So I set up my brackets with 3a and a is the only way I can do it. The only factors of 4 here are either 2 and 2 or 1 and 4. And so a little bit of considering here. If I put in a plus 2 here and a minus 2 here and check the outside and inside terms, you'll notice I do get to plus 4a, which means then that a has to either be equal to negative 2 or a has to be equal to 2 over 3. So I've got my a's, and now I want to work out my lambdas. Remember, my lambda formula was quite easy to work with. It was lambda is equal to 1 over a plus 1. So we now just put in the a values. It means lambda is equal to 1 over minus 2 plus 1. And that means lambda is going to be equal to negative 1. So that's my one set of answers, these two together. And if a is equal to 2/3, then we get the same idea, 1 over 2/3 plus 1. It's a bit of fraction work. This is 3/3, so that's going to be 5/3. And therefore lambda is equal to 3 over 5. And that gives me my second pair of answers, 2/3 and 3 over 5. Okay, so you can have a look through the mark scheme here. Again, there is an alternative method here in order to work with this particular question. I do like this idea of comparing real imaginary parts, because you see this process a ton. If you do work on partial fractions, again, you see that idea again and again with this kind of procedure. Okay, on to the second section here, which is iterative methods. It's actually one of the easier parts, although you have to obviously use a calculator in order to do this, and obviously have a good knowledge of how actual functions look before you can actually use the iterative procedure. So let's start with this one here. So we've got question 6. So sketching a suitable pair of graphs. So you do need to know your graph sketching. Show that cot x is equal to 2 minus cos x, and that has one root in the interval between 0 and pi over 2. So let's start drawing our graph here. So again, nice set of axes. Obviously you're using a ruler at home, of course. So we've got x and y. And again, we're doing this between 0 and pi over 2. So let's put that there. Now the cot graph, if we actually look at the y equals cotangent of x, again, it has an asymptote at the y-axis. And you'll notice as we go down, it actually goes through this point pi over 2. Again, you just need to know that off by heart, the cot graph, the cosec graph, sec graph, and of course sine, cos, and tan from what we've done before. Now we need to show there's one root in the interval between them. So let's have a look at this right-hand side, which is a bit more tricky to work with. So we've got y equals cos x. So let's just start with the function itself. So a quick reminder of what this looks like, again, working between 0 and pi over 2. So generally speaking, we start at 1, and then we go down and then up here. So this is going to be equal to pi over 2. This here would be pi. Again, we don't need this part, but just to get you back in the swing of drawing these sketches, and then finally over here at 2 pi. However, we've got two things going on here. First of all, we have a negative cos x, so that's going to have a reflection effect, and that's going to be in the x-axis. And then we've got the plus 2, and so that's going to translate it, so it's going to shift it up by 2 as well. So with that in mind, we've got 1 being reflected, so that goes down to minus 1, and then goes up by 2, so we need to pop in 1 here. If we take this particular point here, well, this is at 0, it gets reflected, it's still at this point, and then goes up by 2. So a pi over 2, it's going to be, let's mark in, say, 2 here. And so our graph here is going to go something that looks like this. So a slight curve here. Remember, the cot function goes off to infinity pretty quickly. So it's going to go in this direction. And we can see from the diagram that we've done, I would always label this. So this is y equals cos x. This is a sketch of y equals 2 minus cos x, that the graph only crosses 1 here. So we only have one intersection point here. And 2-mark question, it shouldn't be anything too complicated, but you really do need to know your trig graphs and also these new graphs on Pure 3, which is cosec, sec, and cot. After that, we need to show by calculation that this root lies between 0.6 and 0.8. So if we copy this across, we've got cot x is equal to 2 minus cos of x here. Now, the key thing is making sure your calculator is in radians. I'm going to put this in big letters, radians, because otherwise bad things are definitely going to happen to you on your calculator. So the first thing I'm going to do here is put in 0.6. So we're going to work out cot 0.6 is equal to 2 minus cosine 0.6. So let's go to my calculator and work this out. So I've got a normal class whiz here. Again, notice it's set in radians. It says it up here. So make sure that you are aware of it. Now, of course, cot is not on my calculator, but we can work this out by knowing it's a reciprocal function of tan. So we do 1 divided by tan of 0.6 in radians. That gives us 1.46. So let's pop that down. 1.46. Okay, and then we put in 2 minus cos 0.6, and let's pop that in. So we've got 2 minus cos 0.6, that's 1.17. You're thinking, okay, what we kind of want to show here. Obviously, 1.46 here is greater than, I can't remember it out anymore. Oh, that's annoying. Is greater than 1.17, and now we're going to do the same with cot of 0.8 and 2 minus cosine of 0.8. So we do the same process here. So I come to my calculator, I'm going to type in, let's give myself a bit of space, 1 divided by tan of 0.8 That gives us 0.97. This is why these are sort of easier questions here, really. It's just it takes a bit more time. Under time pressure, it's not much fun. So 2 minus cosine of 0.8, and we put this in, and we get 1.3. Now, what's the point of me doing this? Well, notice we have a sign change here, yeah? So 1.46 was greater than 1.17, and 0.97 is now less than 1.30. So we have a change in inequality here. So that means the root then lies between 0.6 and 0.8 to give us our 2 marks. And now luckily we're given the iterative formula here, so we don't actually have to work this out ourselves manually. So we've got x equals xn plus 1 is equal to tan inverse of 1 over 2 minus cos xn, and we need to use this to work out the root correct to 2 decimal places and give the result of each iteration to 4 decimal places. Okay, so first of all we want to set up what number we want to use. So we have number, again, nice clear table here. And then we have our process, and then give myself a bit of space here, and then conclusion. So what conclusion we're going to make from the result that we have so far. So we know it's between 0.6 and 0.8, so let's try 0.7 here. So we're going to try 0.7, then we're going to do tan inverse of 1 over 2 minus cos of 0.7. So if I go to my calculator, and just be very careful as we type this in. So we've got shift tan inverse, like my fraction button, 1 over 2 minus cosine of 0.7, 2 lots of brackets, and we get 0.6805. Result of each iteration in 4 decimal places. Okay, so that's our next one. And then we can use this, so 0.6805, so we have the same working here, minus cosine 0.6805. And again, what we can do with the calculator, which is quite a useful tool here, is we can use the answer key. So what I'm going to do here is go shift tan, we type in what we did before, 1 over 2 minus cosine of answer, because it's iterative formula, so we want to use what we did before. That gives us 0.6855, 6855 dot dot dot. And again, we'll use this once more because we want to determine the root correct to 2 decimal places, but I always do like a double check afterwards. So now we put in this one. Again, it's only 3 marks, so we want to try and keep this as efficient as possible. 0.6855. And now I've got the answer button, I can just press equals, makes things very much easier, and we get 0.68425. 0.68425. And we want the root correct to 2 decimal places here, so notice we are getting 0.68 here. So I think we can pretty comfortably say here to 2 decimal places, I'll show you the answer here, of 0.68. Again, having that justification here by using this iterative procedure to make sure that we can actually get to the answer that we are looking for. Okay, and on to question 8 here. So again, sketching a suitable pair of graphs, we need to show that this only has one root. Okay, so let's draw out our axes. Now the great thing about the square root function, again, we can't have anything below the x-axis. Negative square roots are only complex and not real. So if we have y and x, the square root of x function is quite an easy one to draw. It looks like this. Again, the function you simply just need to know how to draw here. Now e to the power of x minus 3, let's have a little think about this. Now the e to the power of x function looks like this. So it goes through at 1. and then goes off to infinity upwards like this. But we've got a -3, so that's going to shift the graph 3 downwards. So what we're going to get here is actually going to now go through 1 minus 3, so -2, and then we get our graph. It's going to go to infinity pretty quickly. So notice far more quickly than the square root of x does, and notice we only have one root. We've only got one intersection point between these two graphs. So again, I give you lots of different kind of graphs on Pure 3, so you really need to be happy with not only sketching the basic functions, but sometimes doing some of the transformations of graphs from Pure 1 to help you work out there's only one root. Now, from calculation, we need to work out the root lies between 1 and 2. So let's copy out our function here. Root x is equal to e to the power of x minus 3. And so we're going to try 1 first of all. So we get root of 1, which is just 1. And then we're going to get e minus 3. Shouldn't put the equal sign straight away because we are going to work out what's going on between them. And if we do e minus 3, let's work out what that looks like. So again, you should have your trusty calculator ready here, and we're going to use the e function, so shift and natural log button, and this is just e to the power of 1 and then minus 3. That gives us minus 0.28. So it's going to be minus 0.28. So 1 is obviously bigger than that, and now we put in the 2, so the root of 2 is roughly 1.41ish. And if we work out then e squared minus 3, so back to our calculator, I do not know that mentally. So if we go e, not natural log, I'm sure we'll deal with natural logs later, e squared minus 3, and we get 4.389, so we get 4.389, which obviously is bigger than 1.41, so we have an inequality change. So therefore, root between 1 and 2, which of course we're going to work out a bit more thoroughly a bit later on. Now on to question C, which is a bit different to the question we did before. So show if the sequence of values given by this iterative formula converges, it converges to the root of the equation in A. So essentially, how is this linked to the basic equation of root x is equal to e to the power of x minus 3. So they can set up different iterative formulae here. So we need to get the one that matches what we have here. Now what I'm going to do, because there's different ways of making x the subject, we could square both sides, or we could try and isolate the one next to the e. So that's what we're going to do here. So we add 3 on both sides, so we get e to the power of x equals 3 plus root x. Notice it's now looking very similar to what we have here. And now the opposite of the e function is the natural log. So we're going to do the natural log on both sides. And if we do that, this cancels, and we're left then with x is equal to the natural log of 3 plus root x, which we again write iteratively as x n plus 1 equals the natural log of 3 plus the square root of x n, which gives us exactly what we are looking for here. And of course, we're actually going to have to use this iterative formula here to calculate the root correct to 2 decimal places, and then each iteration to 4. So we set up a very similar table to what we did before. So we're going to have our value, which we're going to use. Let's set up a nice table. Of course, you draw a nice pretty table in the exam. And then we have our process. And then we have our conclusion. So we use from there, or the value that we generate. So we're doing this between 1 and 2. So if we don't know really anything going on so far, I'm just going to take 1.5 as a reference point and use this formula. So we have the natural log of 3 plus the square root of 1.5. Certainly I can't do that in my head. So let's put down this value. So again, we are using natural log button. I told you we'd use it a bit later on. So we've got a natural log of 3 plus square root of 1.5, which is going to give us an answer of syntax error, which is not good. So, okay, let's go back because we're putting brackets in the wrong places. So there we are. Use the arrow key, and there we are, 1.440. 1.440. Notice 4 decimal places with the iteration, and so we're going to now use 1.440 in our next iteration, like so, writing in the steps. And so we go back and we can use that handy answer button. Now it's going to make our life a lot easier. So we have the natural log of 3 plus the root of answer, put in the bracket in the right place, and that gives us here 1.43517. 43517, which is going to be our next answer. Again, I have no idea what the answer was going to be, but saying starting at 1.5 kind of makes sense. So we can try and get to the answer as quickly as possible. 3517. I think I've shown enough steps at this point, so we can keep pressing the answer key at this point, and notice we get closer and closer and closer. We only need it to 2 decimal places, and I think it's pretty clear we're going to get to 1.43 as our final answer to 2 decimal places. So again, you don't need to put down lots of steps here, but you do need to show that you understand this iterative process and can work through this process. So you can have a look through the answers here, and you can see where we picked up all the marks for this question here. Question 8, a bit later in the exam, but again, I think these are fairly easy marks to pick up compared to some of the other topics you're going to see in this video. Okay, and on to one of the biggie topics on Pure 3, of course, that is differentiation, then followed by, obviously, its twin, integration. And the first question here is one of these sort of big 6-marker style questions where they just give you an expression and you need to find the exact coordinates. So when you're working in terms probably surds or in terms of e, things like this, of the stationary points of this particular curve. So the issue is not like what to do in this particular question, it's actually just doing this very carefully. Now notice we have a fraction, so we have a quotient, in other words, so we're going to use the quotient rule in order to differentiate this. So first of all, we make the top equal to u, so u is equal to 3x squared plus 1, and then v is equal to 1 minus x squared, and we're going to differentiate both here. So if I differentiate u here, remember we're using the chain rule here, so differential of 3x squared, that's equal to 6x, and then we keep the e stuff alone. So we leave it as e to the power of 3x squared plus 1, and v dash here is just going to be minus 2x. Now we put this into the rule, so for dy by dx, remember, for the quotient rule, different to the product rule, we've got vu dash minus uv dash all over v squared. So if we substitute this in, we have vu dash, so these two multiply together. So we have 6x brackets 1 minus x squared, e to the power of 3x squared plus 1, minus uv dash, so it's going to be a plus 2x, e to the power of 3x squared plus 1, all over v squared, so that's going to be equal to 1 minus x squared, all squared. So we have our expression here. However, we're looking for the stationary points. I could do some more tidying up, but I know we're looking for stationary points. If I see that phrase, then I know our derivative, just like in Pure 1, is equal to 0. And if a fraction is equal to 0, then the top of the fraction must be equal to 0. That means then that 6x, 1 minus x squared, that horrible thing on the top here, is equal to 0. The hardest bit is to write all this out. Plus 1 is equal to 0. Now, the way to go about this, particularly with e functions, you'll see this quite a lot. We take out this factor that's shared here. So we have e to the power of 3x squared plus 1. Whatever we're left with, we put in the second bracket. So 6x, 1 minus x squared plus 2x is equal to 0. And we use the idea of quadratics, which is if you have two things that are multiplied to give you 0, then one has to be 0. Now notice this function here, this e function, can never be 0, and this is often a trick you'll see on Pure 3. Therefore, that means then that this part, the 6x brackets 1 minus x squared plus 2x, must be equal to 0. Therefore, we only are concentrating on this part here, so 6x 1 minus x squared plus 2x is equal to 0. And like lots of things in mathematics, it all comes back to quadratics. So if we solve this quadratic, So we have 6x minus 6x cubed. Let's double check what we're doing here is equal to 0. That gives us then minus 6x cubed plus 8x is 0. So we can take out a couple of factors here. We can take out an x and we can take out a 2. That then gives us minus 3x squared. You can double check all the algebra here. Plus 4 is equal to 0. That means then that 2x is 0, so x is 0, so that's one solution, so pop that over there. Or minus 3x squared plus 4 is 0. That means 3x squared is equal to 4. X squared is equal to 4 over 3. And of course, we square root, we get plus and minus, so plus minus. That's going to give us 2 over root 3, which we can rationalize here. Notice all these basic skills like iGCSE and Pure 1 really speeds up this kind of process. So we get plus minus 2 root 3 over 3. So that gives us our 3 solutions, our 3 stationary points here for this particular curve. However, we're not finished because we want the coordinates. So we also need to work out the y. So when x is 0, so this should make things a bit easier, y is equal to e e to the power of 1. I think I wrote this down incorrectly. It doesn't make any difference though. Yeah, so this was a minus 1, but it keeps pretty much all the working the same here. So that gives us e to the power of minus 1 over 1, so that's just equal to e to the power of minus 1. Okay, that's all good. So we have that coordinate, 0, e to the power of minus 1. If we now put in 2 root 3 over 3, let's start with a positive. So 2 root 3 over 3, and put this in. It's going to make no difference whether it's plus or minus because we're squaring the x each time. So we'll get the same value. So actually I can just put in plus minus here. We'll get the same value of y. So we have e to the 3 lots of 2 root 3 over 3 squared minus 1 over 1 minus 2 root 3 over 3 squared. Now, if I'm in an exam, we can just put this into the calculator as well. Don't necessarily need to solve this manually. So let's just do this as a bit of practice. So we've got shift E. We've got 3 lots of 2 root 3 over 3. Notice I'm always looking for ways to save time here. Notice we can do plus minus essentially at the same time. Minus 1. And can we now make this a fraction? Yep. So let's just double check everything's right here. 1 minus, and then 2 root 3 over 3, bracket in the right place, squared. Okay, and that gives us some strange value of minus 60.26. But looking for exact coordinates. So if you do exact coordinates, we have to do this manually. Okay, that's kind of annoying, but not a problem. Let's create a new slide. So we've got a bit of space to work this out. So we have y equals E3. Sometimes the calculator will actually work it out for you with exact values, depending on your model. So that's something to consider. So 2 root 3 over 3 squared. Okay, let's think about this. So we've got times in by itself. So 2 root 3, that's equal to root 12. So we get 12 over 9, 3 lots of 12 over 9 minus 1. And then 1 minus this squared. So 12 over 9. So that gives us e cubed. Okay. Over 1 over 12 minus over 9. So minus the third, and then that's going to simplify to minus 3 e to the power of 3, and that's going to be the same for both. Yeah, perfect. So our final answers here, let's summarize all this together. We have 0 e to the power of minus 1, and then we've got the positive version, so 2 root 3 over 3 minus 3e cubed, and then we've got minus 2 root 3 over 3, and it's the same answer because we have squareds in the function there to give us the 3 stationary points and for all 6 marks. So you can have a look through the mark scheme here. Yeah, not very helpful, and this is why these videos are out here for you, to really go through that step by step to see exactly how we're getting to the answer. Right, on to question 7, slightly different here. So we've got an equation of a curve. Now notice this is in x's and y's, so it's not just y equals. So we've got it in terms of x's and y's. So that means we're going to have to use a process called implicit differentiation in order to differentiate this, which is a fairly easy process. It's just to be aware that this is going to happen. So if I differentiate this, we essentially approach it normally. So x cubed becomes 3x squared. If I differentiate anything with y, I differentiate it normally, so that's 2y, but then I put a dy by this dx after it. 3x squared, that's just 6x. 3y, that's just going to be 3 dy by dx. And that's going to be equal to 0. Remember, any number here is just going to differentiate to 0. At this point, I'm going to put all the x's on the other side and leave the y's where they are. So 2y dy by dx plus 3 dy by dx is equal to, and we'll take out a minus out of both, so 3x squared plus 6x. And now I can factorize with dy by dx because they're shared. And that leaves us then with 2y plus 3 equals minus 3x squared. And we'll try and make it look like what the question has, and then divide through by 2y plus 3. So dy by dx is then equal to minus 3x squared plus 6x all over 2y plus 3, which is one of those lovely show that questions and feels very good for the 3 marks. Now from that, we need to then work out, so even if we didn't get that, we can still use it in part B, the coordinates of the points on the curve at which the tangent is parallel to the x-axis. Now, it's kind of weird language here, but if you think about this, if I've got a graph and it's parallel to the x-axis, then it's just a horizontal line. And a horizontal line, we know, means that the derivative is equal to 0. So it's another way of basically questioning, okay, the derivative is equal to 0. Now, if we have a fraction equal to 0, that means the top has to be equal to 0. So that means then that the minus 3x squared plus 6x must then be equal to 0, which means basically that 3x squared plus 6x is equal to 0. Again, we can take a factor of 3x out here, and that leaves us then with x plus 2. And therefore either x is 0, so that's one answer, or x is equal to minus 2, which is our second answer here. However, we need to work out then what the y values are. So it's a 5-mark question, so it can't be as easy as this. So we'll do x is 0 first. And notice we've got the function here in terms of x's and y's. So when x is 0, that then leaves us with y squared and a 3y is equal to 4. Okay, that's just a quadratic to solve here. Okay, and everything just leads back to quadratics. This actually factorizes nicely, which is pretty handy. So we have a plus 4 minus 1, all looking good. And therefore y has to either equal 1 or minus 4. So this is our first answer. When x is 0, then we have either 1 or minus 4. And now when x is equal to minus 2, then we put it into our function. So we have minus 8 plus y squared plus 3x squared. So that's 412 plus 3y is equal to 4. Okay, so that gives us a quadratic of y squared plus 3y is 12 minus 8 is 4, 4 minus 4 is 0. Okay, that's nice. So we get then y brackets y plus 3 is 0, and therefore y is equal to 0 or minus 3. So if when x is minus 2, then the two answers we get out of it is equal to 0 and minus 3. Not particularly that difficult question for 5 marks, but you do need to be precise and be really happy with solving these quadratics quickly. If you were using the quadratic formula each and every time to do this, this would waste a ton of time that you really need for some of the other questions. So you can go through the mark scheme here. This is question 7a and 7b, making sure you're really familiar with all the differentiation ideas. I've gone through quotient rule and implicit differentiation in this short part of the video. Okay, on to the integration part of this video. So we're going to go through two pretty tough questions. Going to be some differentiation involved in this as well. So you're getting lots of calculus practice here. So we've got the diagram here showing a curve of y equals x cos 2x. X is greater than or equal to 0. And we want to find the equation of the tangent to the curve. So as soon as I see this, I'm thinking, I need to do my dy by dx here at the point where x is equal to pi over 2. Okay, so the first thing we want to do here is differentiate this function x cos 2x. This time I'm going to use the product rule. I haven't used it so far in the video. So that means our u will just be equal to x, our v will be equal to cos 2x. And then we need to differentiate both here. So u dash is equal to 1. And v dash, again, we've got our chain rule kind of embedded here. So we bring the 2 to the front. And if we differentiate cos, we're going to get minus sign. So we get minus 2 sine 2x. Now we're going to go and work out dy by dx. Again, important to know your rules here. So we have uv dash plus vu dash, which means uv dash, so it's these two multiplied. That gives us minus 2x sine 2x plus vu dash, so these two multiplied, which is just cos 2x. And we want to work out the derivative here, so the gradient at this x is equal to pi over 2. So we want to work out d of dx, where x is equal to pi over 2. So we put it into our function, so we get then minus 2 pi, because pi over 2, sorry, minus pi, because we get a cancellation here. So let's try write that again, minus pi sine, and then 2 times pi over 2, that's just sine pi, and plus cos, well, 2 pi over 2 is just pi as well. So remember, pi here, again, you have to work in radians. So pi radians is equal to 180 degrees. So again, you can use your calculator to check this, but this term is going to disappear, and then we're going to get a -1 for this. Again, really useful to know the non-calculator like cos 180, sine 180. It's going to save you a ton of time in the exam. So that means then we get the equation of y equals minus x plus c. However, we still need to work out the y-intercept here. Now, what we can do at this point is we've got the x value. So when x is equal to pi over 2, we can work out our y value at that point, substitute it back into the original function. So we get pi over 2 times cos of pi. Again, double checking we're putting everything in correctly. So the cos of pi, we already worked out that was equal to -1. So -1 times this is just going to be minus pi over 2. So we put this into our equation. So when x is pi over 2, y is minus pi over 2. That gives us then minus pi over 2 is equal to minus pi over 2 plus c. Okay, we get a nice cancellation here. So c is equal to 0. Therefore, our final answer is equal to y equals minus x, which you could also write in different ways. You could write this as x plus y is equal to 0 as well. And that gives us the tangent line at that particular point at pi over 2. So a nice question here, mixing up a bit of working with radians and trig functions, but also your product rule as well. Okay, and now we need to find the exact area of this shaded region. So if I go back here, this region down here, in the diagram bounded by the curve and the x-axis. Again, as I've labelled here, as soon as we see area shaded region, we know there's going to be some integration. Now, before we can actually do any integration here, notice we're looking for this small area here, and we're going to need to find one of these roots here in order to work out exactly where we're going to integrate from. So we take our function x cos 2x is equal to 0, then either x is 0, which we kind of knew already because it goes through the origin, or cos 2x is equal to 0. So we've got a little equation to solve here before we can actually work out the integration. And if we do the inverse cosine of 0, again, think about what your cosine function looks like as it goes to 0. Well, it intercepts at pi over 2, so 90 degrees, 3 pi over 2, and then keeps going up in 180 degrees. But we're not looking for every answer here. If we divide each side by 2 here to work out the value of x, we have then pi over 4, 5 pi over 4, and so on. So the first intersection point here with the x-axis is equal to pi over 4. So now we actually work out the limits of our integration. We want to integrate this function between 0 and pi over 4. So now we know pi over 4 is the intersection point. Then we can actually work out the integral of pi over 4 to 0 of our initial function, which was x cos 2x with respect to x. Now, there's lots of integration techniques. Again, one is by recognition. Again, that's not very obvious to do here with two functions of x. Substitution, there isn't a natural substitution to try and change this, something that we can integrate. So we need to look instead at integration by parts. Now, the formula for integration by parts is uv minus the integral of u dash v. However, we have to be careful what we put into our function. Our u here is equal to x, but our v dash is this other function, our cos 2x. So we set it up in exactly the same way, but we have to be a little bit careful. And now we want to work out what u dash and v are. Now u dash is nice and straightforward. It's equal to 1. With this, we need to integrate cos 2x. So we know there's going to be a sine 2x involved because sine differentiates to cos. But now we need to consider this 2 by the coefficient, and therefore we need a half in here. So when we actually differentiate, 2 times a half gives us 1. So we do get a half sine 2x. Once we've got that, then we can put it into our formula. So uv, so a half x sine 2x, minus then the integral between pi over 4 and 0 of u dash v. So we have a half sine 2x. And once we've got that, then we can integrate this separately because now we've got something we can fairly easily integrate. So we have a half x sine 2x, now minus, and now we integrate this. So we need to now have a cos 2x involved. Now we need to think what comes at the front to give us a half, so a quarter. And then we think about the sign, so cos differentiates the minus sign, so this will need to then be a plus. Notice how we're working backwards through this. Okay, and we're working between pi over 4 and 0. Once we got this, then we can just integrate this by putting pi over 4 and 0 into the function in order to generate the final solution for the area. If we put pi over 4 into this, then we're going to get pi over 2 in both of these cases. And notice that cosine pi over 2 is 0, so this term will disappear. So this one over here, we're going to have then pi over 2 for 90, that's going to be 1. So here we're going to get a half times 1. So half times pi over 4 times 1. And then we put in the 0. So if we have 0, this term is going to be the one that disappears. And we're going to be left with this term over here. So cos 0 is 1. And then 1 times a quarter is a quarter. And if we simplify this down, we're then going to get pi over 8 minus a quarter to be our final area. And again, we're always careful to check this, but notice we're going to get a positive area, a small positive area. If we put this into a calculator, we could double check that. Okay, so you can see the mark scheme in front of you, going through the product rule, going through finding the limits, and obviously going through that integration by parts procedure at the end. Okay, on to our next question. So let's move away from some trig and let's look at our exponential function instead. So the diagram shows the curve y equals x e to the power of minus a quarter x squared, and we have a maximum point which we need to find. As soon as I see this phrase maximum point, we need to be thinking of differentiation and then setting to 0. So if we take our function, we're going to use the product rule again. So this time we've got u is equal to x, v is equal to the e function that we have here. If we differentiate, u dash is equal to 1, and v dash, let's be a little bit careful here. So the derivative of minus a quarter x squared, that's going to be minus a half x, and then we have the e function afterwards. And if we put into our product formula, remember, that's going to be uv dash plus vu dash. Again, this nice cross idea is quite useful when doing these problems. Then we're going to get dy by dx is equal to minus a half x squared e to the power of minus a quarter x squared minus e minus a quarter x squared. And like I said before, we're looking for a maximum or a stationary point at the very least, and that's going to make it equal to 0. And we see the same techniques, really important on pure 3, that we can take a factor out of this e function. So we get e minus 1/4 x squared, open brackets, minus a half x squared minus 1 is equal to 0. And the really good thing about these kind of functions is this can never be equal to 0. So we just focus on our quadratic. So minus a half x squared minus 1 is equal to 0. And a little bit of rearrangement here goes a long way to find our answer. Again, as I'm going through this, I'm double checking and I'm going, okay, we've got a minus here, but remember it's plus in our formula, so there should be a plus here. So again, always double checking as we go through. So we get a half x squared is equal to 1. That means then that x squared is equal to 2, and therefore x is equal to, normally it'd be plus and minus root 2, but notice we're only considering x is greater than or equal to 0, so then x is going to be equal to root 2. Not quite finished at this point. Again, it's a 4-mark question, so I'm going to need a bit of room to finish off this question here. There we are. Let's create an extra slide because we need the exact coordinates. Again, exact meaning can't use the calculator directly. We've seen this quite a lot in this video. So when x is equal to root 2, we put it back in our function, and that's going to give us root 2e minus 1/4 root 2 all squared. And that's going to simplify to root 2e. Root 2 all squared is just 2. 2 times minus a quarter is minus a half. So we get our maximum point here of root 2 e to the power of minus a half. Like so, which is a pretty nice 4-mark question here to get us warmed up. However, the integration is coming. Again, as soon as you see an area under a curve, you know it's on its way. And now we need to use the substitution x equals root u, so that's quite useful that we're given the substitution, or otherwise, find by integration the exact area of the shaded region bounded by the curve x-axis and the line x equals 3. Okay, so we're already given the limits here between 3 and 0. That's nice. And we need to put in our function. So we've got 3 and 0. We have x e minus 1/4 x squared. Double check you're always writing the function down correctly. And that's with respect to x. Okay, and we're told the substitution we need to do here. So x is equal to root u. Okay. So if x is equal to root u, then if we square both sides, x squared then is equal to u. Okay, that's useful to know. We are going to have to change here the dx. So we need to take that into account as well. So if we have x is equal to u to the power of a half, then dx by du is equal to a half u to the power of minus a half. Okay, and that means dx can be written as 1/2 u to the power of minus 1/2 du. That's also a useful statement. And I think at this point we can substitute in. We'll deal with the limits as well in a moment. So I'm not going to put numbers there for the start. So x here is equal to root u. And now x squared is just u. And then we put in this part to replace the dx. So we have times 1/2 u to the power of minus 1/2 du. And let's now talk about the limits here. So we had 0 and 3 before. So when x was equal to 0, u would also be 0. And when x is equal to 3, then u is equal to 9. So notice if I put in x is 3 into this equation, then u comes out as 9. So we're now between 9 and 0. We have a cancellation here because this cancels with this. So that's useful. So that leaves us then with 9, 0. I generally change the limits rather than back substitute. So that gives us then 1/2 e to the power of minus 1/4 u du. Okay, and that's going to integrate quite nicely. Here, recognition is probably the easiest way to go. So if we set up our integration here, we know this has to stay the same. So we know e to the power of 1 minus 1/4 u. And now we need to think, what number do we put in front such that we get a half at the end? So if we put a minus 2, that looks good to me, because minus 2 times minus 1/4 gives us a half, and this stays the same. Good, okay, I'm happy with that, between 9 and 0. And now we put in our limits. So we've got 9 here, so that's easy to put in. We just get minus 2e power of minus 9/4. And if we put in 0, that's just going to give us 2. And that gives us then 2 minus 2e to the power of minus 9/4, which gives us our answer there. So a couple of things to be aware of. It gives us the substitution. Sometimes you have to come up with that yourself. And make sure you change the limits. Do not forget to change those as well. So that's important. And then we get it in a form that we can integrate then pretty easily afterwards. Right, so you can see the answer for 9a and then 9b here as well, with an alternative method that you can also take this slightly different approach rather than doing what I've done at the top here. Okay, on to this mini section here on linearizing graphs. We'll have to go through at least one question so you've seen the key ideas here. So here we're told that x and y are related by this particular equation, where a and b are just numbers, so they're just constants, and they've plotted the natural log of y against x and found these particular values. Now you often use log graphs, things like earthquakes, for example, the Richter scale, in order to actually have a graph that you can actually work with and compare earthquakes across the world. So they often use this kind of scale, and we're trying to linearize this and bring this back into x and y. Now if we think generally of the lines on a coordinate graph, we generally think of y equals mx plus c. With x and natural log of y, it's a very similar relationship. We have the natural log of y equals the c, which we just called natural log of a, so it's still related to the y, plus the natural log of b times x. So it's the same idea. It's like y equals c plus mx, but we just have natural logs to take into account. The y-axis is now the natural log of y and not just y itself. Once we've got the basics here, so once we've got this idea, you can form a straight line with this particular equation. I'll put natural log of b in brackets so you can see it's like the m. Then we just put in our numbers. So we have 1 and 3.7. So natural log of y is 3.7 is equal to the natural log of a plus x is 1. That's good. So that just gives us the natural log of b. That's our first equation. And then second equation, 6.46 is equal to the natural log of a plus, in this case, 2.2 lots of the natural log of b. So essentially here they're really testing your log skills and making sure you can actually solve these kind of equations for a and b. Now, key technique with logs generally speaking is we want one log on one side before we then try and raise both sides with e. So what I mean by this, if we take equation 1 here, we can rewrite this as 3.7 equals the natural log of AB. Remember your basic log rules from iGCSE or Pure 1. Here we can do the same thing as well. Remember with logs we can bring this to the back. So we have 6.46 is equal to the natural log of AB to the power of 2.2. Only at this point can we actually raise both sides with the exponential function. So if we do this, this gives us then AB is equal to e to the power of 3.7, and then we have ab to the power of 2.2 is equal to e to the power of 6.46. And now we can actually remove the a's by dividing one equation by the other. So if we do that, we then get b to the power of 1.2. Notice with indices, you're minusing them, equals e to the power of 6.46 divided by e to the power of 3.7. And of course, with roots here, that's absolutely fine. We can take the 1.2th root of both sides. That gives us then b as the 1.2th root of e to the power of 6.46 over e to the power of 3.7. Again, your calculator is strong enough here to work all this out for you. So if we put this into the calculator, we have then go shift and this button here, so we can put in 1.2, and then we just put in e, so we've got the e function, we need a fraction first, e to the power of 6.46 divided by e to the power of 3.7. That gives us then our value of 9.97 for b. So 2 decimal places, does it say? Doesn't say particularly what they want it to. Okay, and then we can work out the a value. Again, I'm just going to take this equation here. So that means a is equal to e to the power of 3.7 divided by our answer 9.97 dot dot dot. And if we put that in, so we pop in, I say pop in quite a lot. If I do, let me know in the comments if that's not too irritating. Divide by answer, and that gives us then 4.06 for our A to 2 decimal places. Key thing to watch out for this kind of question is making sure you can solve these logarithmic equations that come out of these linearizing graph style of question. Again, you can check through the mark scheme here. Again, we've taken this kind of approach, the alternative method, for question 3. I think it's the most natural fit to what we've done so far. Okay, and on to our section here on trigonometry. So similar to the pure one, but we've got now other functions to work with like cot, etc., and the double angle formulae. So there's a bit more to consider. So show this equation, cot squared theta plus 2 cos 2 theta is equal to 4, can be written in this particular form. So when I look at these kind of questions, I notice it's got everything in terms of sign here. So I want to basically take our cot squared theta plus 2 cos 2 theta equals 4, and make sure I can write all of this in terms of sign. That's what I'm looking for here. So my first step here is, well, cot squared theta, that's the same as 1 over tan squared theta. That's useful. And if we've got cos 2 theta, there's a couple of different ways you can write this. But the one that we want to use here is the 1 minus 2 sine squared theta version, because we have sine in it. So we have plus 2 lots of 1 minus 2 sine squared theta, and this is all equal to 4. Okay, so now we've got tan squared theta. I'm like, okay, that's not so helpful. But remember, tan is equal to sine over cos, and so cot is going to be over cos over sine. So we can rewrite this as cos squared theta over sine squared theta. And we can multiply this out, so plus 2 minus 4 sine squared theta is equal to 4. So we're certainly making progress here. Notice I don't want coses here, but I can use my Pythagorean identity. So I can go 1 minus sine squared theta. I'm not really worried about trying to get to our destination so far. I'm just following my principle here of, okay, let's try and get everything in terms of sine, and then we can sort out everything after this. Okay, so at this stage, I can multiply everything by sine squared theta, being very careful to multiply everything. So I get then 1 minus sine squared theta plus 2 sine squared theta minus 4 sine power of 4 theta, because sine squared theta times sine squared theta is sine theta to the power of 4, is equal to 4 sine squared theta. I'm already quite happy because I've got a 4 sine theta to the power of 4, so that's looking good. Okay, let's bring everything to one side. So we've got minus 4 sine theta to the power of 4. Okay, let's collect up all these sine squared thetas. So we've got a minus sine squared theta plus, that's plus 1 minus 4, that's going to be minus 3 sine squared theta. Plus 1 is 0. This is very similar to what we need. And then we just times through by minus 1. So we just get 4 sine theta to the power of 4 plus 3 sine squared theta minus 1 is equal to 0, and that's what we're looking for. So it looks quite intimidating when you first see that question. But again, it's just going, okay, this is what I have. This is what I'm looking for. I want to use all the identities that I know to get everything in terms of sine, and then things will sort themselves out afterwards. Now, usually they have a hence question here. Yep, here we are. So they take that equation that we just did to make sure it's exactly the same. It is. And we need to solve between 0 and 360. So we're taking our answer. So 4 sine theta to the power of 4 plus 3 sine squared theta minus 1 is equal to 0, and solve. And this isn't a very special form. This is like x to the power of 4 plus x squared minus 1 equals 0, that kind of form. And so we can actually think of this as a 4y squared plus 3y minus 1 equals 0 kind of question. And if I asked you to factorize this, this wouldn't be so bad to factorize. We could do 4y and y, and then we want a plus 1 there and a minus 1 there. Okay, so we take exactly the same approach. Instead of y, however, I'm just having a sine squared theta, but it's exactly the same principle. And then we have sine squared theta plus 1 is equal to 0. And now we've got two functions to solve, so it's going to take a bit of time to consider. So if we have the first one and make it equal to 0, that gives us then 4 sine squared theta is equal to 1. Sine squared theta is equal to a quarter. If we square root, sine theta is equal to plus minus 1 over root 2. Okay, that's a nice exact value. And if we do the same with this one, we have sine squared theta is equal to minus 1. And if we try and square root this, again, we don't get an answer here. Okay, so we're only going to be focusing on this part here. So 1 over root 2. So we get sine squared theta is equal to a quarter. Therefore, we square root of this. We're going to get plus and minus a half. That's very helpful. Okay, so what solutions do we have between 0 and 360? Well, our principal solution, and it's in degrees, is equal to 30 degrees. That's our exact values. And if we think, again, you can use cast diagram. So we've got 30, then we're going to have 150, 210, and 330. So we're going to have 150 degrees. Again, lots of detail in my Add Maths video. Feel free to check that out above. So you get 150 using our cast diagram, 210 and 330 degrees between 0 and 360. If we try and solve the second one, that gives us sine squared theta is equal to -1, and yet that's not going to be a solution because we can't work out the square root of -1 with our real numbers, and therefore our only solutions are going to be 30, 150, 210, and 330. Okay, so you can check out the mark scheme here. Again, lots of different ways of doing questions, 6a here, and with 6b. Again, it's getting that quadratic and being really comfortable from what you've already done with trigonometry to then solve those trig equations when they come out. Okay, on to my section on differential equations, and this is a real hard one. Okay, so one question in this section, but it's going to take a while and a lot of different skills combined. So we have the differential equation here, x squared dy by dx plus y squared plus y is 0. We're given x is 1 and y is 1. And we've got to solve it first of all, which is going to take a bit of time. And then we have to do a bit of log work to get an expression for y in terms of x. Right. So first thing I'm going to do is I'm going to put all the y's on one side, all the x's on the other. That's our general strategy for doing separation of variables, which is what we're going to do in a moment. So I'm going to put here minus y squared plus y on this side. And now the key thing to do here is making sure we put all the y's on the left hand side and all the x's on the right. I'm going to keep the minus over here with the x. So when I divide through, I'm going to get 1 over y squared plus y dy by dx is equal to minus 1 over x squared. So what I've done to go from step 1 here to step 2 is divide through by y squared plus y on both sides, and then divide through by x squared on both sides, keeping the minus over here because this is going to be a fairly easy thing to integrate. Now, to do the separation of variables process, we're going to integrate both sides with respect to x. So I'm going to add an integral sign and add a dx. Now, the great thing about this separation of variables method is these dx's cancel, and so we're left on the left hand side with 1 over y squared plus y dy. So we can integrate in terms of y, no changing variables there. And then on this side, we're just going to integrate normally. Notice minus 1 over x squared is the same as minus x to the power of minus 2. Now that's really easy to integrate here. Remember, we add 1 to the power, divide by the power. So that's going to give us here x to the power of minus 1. Again, we're not going to worry too much about that side for the moment. Again, I'm going to put a plus c because, again, we have a constant integration of some kind. The tricky part is integrating this left-hand side, which is a bit uglier. So I'm going to do that over here. So we've got 1 over y squared plus y with respect to dy. And the strategy we're going to take here is use a bit of partial fractions. So notice I can rewrite this as y brackets y plus 1. And what I'm going to do is separate this out into two fractions. So remember, this is always equal to a over y, where we don't know what a is, plus b over y plus 1. The reason for this is then we can integrate both with the natural log, and it's going to make our life a lot easier. Now, in order to work out a and b, I'm going to times by the denominator. So I'm going to get 1 over here. And I've times by y already, but not y plus 1. So I'm going to get a brackets y plus 1. Plus over here, I've times already my y plus 1, but I've also got y. So this becomes by. If I expand out the brackets, I get ay plus a plus by. And now we're going to compare our coefficients. Notice we've got an a here and a b here for the y, and there is no y over here. So that means then a plus b, the coefficients of y over here, is equal to 0, and the number left over, a, must be equal to 1, which is a really easy equation to work with here. If we know a is 1, then therefore b must be minus 1 in order to get 0. So what I've done here is I've transformed this into 1 over y minus 1 over y plus 1 dy. So with this partial fraction result, I can go back. This is a real doozy of a question, by the way. So we get 1 over y minus 1 over y plus 1 dy. We've already integrated the other side. And here we can integrate really easily because 1 over y is just the natural log of y. And here we've got the natural log of y plus 1. And the constant of integration will compensate for both sides of this. So we've broken it down to something that actually integrates quite easily. We're not even close to finishing yet. So let me write this down. So natural log of y minus the natural log of y plus 1 is equal to the x power of minus 1 plus c. Now we have our initial conditions. X is 1 when y is 1. So when x is 1, y is 1. So that means then we have the natural log of 1 minus the natural log of 2 is equal to 1 plus c. Notice natural log of 1 is just equal to 0. You can check on your calculator. And the minus here we can bring to the back, and that gives us natural log of 2 to the power of minus 1 equals 1 plus c. And natural log of 2 to the power of minus 1 is the natural log of a half equals 1 plus c. And therefore c itself is equal to minus 1 plus the natural log of a half. So if we put that back into our equation here, we're then going to get, I'm going to need more space, the natural log of y minus the natural log of y plus 1 is equal to x to the power of minus 1, and then what we just did, so minus 1 plus the natural log of a half. Now, if only we could just leave it in this form and just go, yeah, we've solved it, we've got y's and x's in places, then that'd be really, really good. However, we want it, to go back to the question, y in terms of x. So we need it as y equals something at the end. Okay, so the way we approach this, again, anything with natural logs, you've seen this I think in the previous section, is we want natural log equals natural log, then we can cancel. So the left-hand side's fairly easy. We can just write this as y over y plus 1, minusing with dividing. And it's about tidying up this part here, which is a little bit more on the tricky side. What we can do is we can actually add in natural logs here. So we have natural log of e to the power of x minus 1. Notice x power of minus 1, so that's not that clear. So there's a power there as well. So all I've done here is I've added a natural log and an e, and notice those would cancel to get back to this. So I'm kind of unsimplifying it. I do the same with the next part. So natural log of e to the power of minus 1. Right, let's tidy this up a bit. So I'm just adding a natural log and an e next to it so we can get it all in terms of a nice log that we can work with. Okay. Then once we've got that, then we can start combining these logs together. So if we are, let's pop this bit over here. Now we've got these, we're just multiplying the things together. So we have the natural log of e to the power of x to the power of minus 1 times e to the power of minus 1 times a half. Again, remember adding is the same as multiplying, and now we can actually start getting rid of these natural logs. So we raise everything, so we get y over y plus 1 is equal to e. Let's just write this as 1 over x, that's probably easier to look at, times e to the power of minus 1 times a half. Okay, and now we just need to rearrange this to make y the subject. So the way we do this, we're going to multiply by the denominator. So we have y plus 1 times a half e to the power of minus 1 e to the 1 over x. Okay, so we're going to have to expand out the bracket here. So we have a half e to the power of minus 1 y e to the power of 1 over x plus whatever this is already, e 1 over x. And now we bring this to the other side, so we get y minus a half power of minus 1 e to the power of 1 over x is equal to a half power of minus 1 over x. Okay, I'm going to combine some of these indices already. Then we take out a factor. I'm probably going to need more room. Yeah. So we have y open brackets 1 minus 1 half power of minus 1. We've taken a y out, so e to the power of 1 over x is equal to whatever was there before, minus 1 over x, and then we divide through, so then we get y equals a half e 1 over x. I'm going to tidy all this up at the end, 1 minus half 1 over x. I'm sure they would accept this, but we can times top and bottom by 2 here. So that gives us then e to the power of 1 over x minus 1 over 2 minus e 1 over x minus 1. We can put these indices together, which then gives us our final answer for 1 mark. It'd be interesting to see if they've kind of left it in this kind of form, whether they give you all 8 marks. But we're doing a little bit of tidying up here. So this part here, remember, e to the power of 1 over x times e to the power of minus 1. We're just adding the indices here, yeah? So we're just doing 1 over x minus 1. If you times top and bottom by 2 here, of course, that doesn't change anything. Okay, that was a bit of a doozy of a question. Again, you probably can't even see the answer down below. A lot of different things in that question. So even though we're focusing on separation of variables, which is what we did here, there's partial fractions in here, there's log work as well. And really to do well on Pure 3, you really need to be comfortable working between the different topics. You can't just say, I'm really good at upper and lower bounds, but I'm not very good at probability. It's all tying in together. And that's the key thing with differential equations. Okay, and on to parametric equations, which sound quite tricky, but actually are just using the chain rule and everything you've already done with differentiation. So here we've got x and y written in terms of another variable, so t in this case, and we need to find dy by dx. So whenever you're working with parametric equations, you generally want to differentiate in terms of the variable given. So if we take x is equal to t to the power of a half plus 3, then if we differentiate, we get dx by dt, which is equal to a half t to the power of minus a half. And if we do the same with y is the natural log of t, then dy by dt is equal to simply 1 over t. Now, the chain rule that we're going to use is the following. If we have dy by dx, this is the same as saying dy by dt times dt by dx. It's kind of unsimplifying it. And notice we could cancel the dt's here to give you dy by dx. So if we use this formula, dy by dx is equal to dy by dt, so 1 over t, times dt by dx. Now if dx by dt is this, then we simply want to flip it. Now this can also be written as 1 over 2 root t, which might be easier to work with. It's the same thing. So if we flip this, we're just going to get 2 root t over 1. And this then just gives us 2 root t over t. Again, this can be simplified in a lot of different ways. Again, we can think of it in terms of indices. And this would then give us 2t to the power of minus a half to give us our expression in terms of dy by dx. Now, b is a nice little twist on this because you want to find the exact coordinates. So again, precise in terms of natural log, in terms of roots, of the point on the curve at which the gradient of the normal, so watch out for this, is minus 2. So if the gradient of the normal is minus 2, the gradient of the tangent is going to be the negative reciprocal, which is 1 over 2. So this is saying, in other words, that dy by dx is equal to a half. And we just worked out dy by dx. We worked that out to be 2t to to the power of minus a half. So these two things must be equal to each other. Once we have this, we can solve the equation. We divide by 2. T to the power of minus a half is equal to 1 over 4. We can remove the negative of the index by flipping the fraction, so we get 4. And if we square both sides, we're then going to get 4 squared is equal to 16. Now, t being 16 is not the answer because we have x and y in terms of t. So if I write this down again, x is equal to root t plus 3 and y equals the natural log of t. We can now work out the x and y values, the coordinates, by substituting our value of t into x and y. So therefore x must be equal to the square root of 16 plus 3. So that's 4 plus 3, which is equal to 7. And then y is just equal to the natural log of 16. So the coordinate, where the gradient of the normal is minus 2, is simply just 7 and the natural log of 16. Exact because we're writing it in terms of natural log. Okay, so you can have a look at these solutions here and see how we've been using the chain rule to work with these parametric equations. Okay, and on to the vectors part of the course. Yes, it's time for more practical topics. So we've got two vector equation lines here. So we've got the position vector and direction vector for L and M, and C is a positive constant, and we're given the angle between them is 60 degrees. As soon as I see the angle between two vectors, the first formula that comes to mind is the scalar product formula. So A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle in between them. So whenever we look at the angle between two vectors, we only really care about the direction vector. So it's this vector here. So if we do the A dot B first of all, and we only care about the direction vectors, so we're doing 1, 1, 2 dot minus 2 for C. And that will give us, here we are, minus 2 plus 4 plus 2C. So this simplifies then to 2C plus 2. Then we want the magnitude of A and B. So the magnitude of A, so it's just the magnitude. So Pythagoras on 1 squared plus 1 squared plus 2 squared, which is the root of 6. And then the same for B, so the square root of minus 2 all squared plus 4 squared plus C squared, which gives us the square root of 20 plus C squared. And now we can link it all together. So that means then 2C plus 2, our dot product, is equal to root 6 times the root of 20 plus C squared times the cosine of the angle in between them, which is 60. Now notice they've used a nice exact value here. So cosine of 60, of course, is equal to a half. That's going to make life a lot easier later on. At this point, I think I would just times by 2 to remove the half. That gives us then 4C plus 4 is equal to root 6 times the root of 20 plus C squared. And now I'm just going to square everything here. So if I do that, I'm going to be squaring this. That gives us then 16C squared plus 32C plus 16. Now squaring this gives us 6 times 20 plus C squared. The square roots disappear. We're getting a quadratic. Well, we're looking for one value, so if it's positive, that kind of makes sense. So that gives us then 16C squared plus 32C plus 16 is equal to 120 plus 6C squared. Bring everything to one side again. It's always quadratics every single time. Yeah? So 10C squared plus 32C minus 104 is equal to 0. We can divide through by 2 here. 16C minus 52. And this is where we hope it factorizes. Generally speaking, this video so far, they've been pretty nice. So we've got 5C and C, 52, 13 and 4, 26 and 2. 26 and 2 I think works. So we have plus 26 here and minus 2. Yep, that gives us a plus 16. And we only want the positive answer here, positive constant. So then C, after all that effort, is just equal to 2. So key thing in this question, as soon as I see angle between two vectors, this is the first formula that's like neon lights in my head before then I get started on the question. Now 10b, show the length of the perpendicular From 6 minus 3, 6 to L is root 11. Okay, for 5 marks. So I see length of perpendicular. So as soon as I see the word perpendicular, I'm thinking of the dot product being 0, so at 90 degrees to each other. Before we do that, we need to find between L, which is our first equation. So let's just write out L in combined form. So what I mean by this is 3 plus lambda minus 2 plus lambda 1 plus 2 lambda. And so what we need to do is find the vector between this general form and 6 minus 3, 6. So we need to take one away from the other. That then gives us minus 3 plus lambda, careful here with negatives, 1 plus lambda minus 5 plus lambda. Okay, so this is our vector A, what's the point called? Yeah, let's just call it AL. And we want this to be perpendicular to the direction of L. So what that means is we want this vector, 1 plus lambda minus 5 plus lambda, the dot product with the direction vector, which is 1, 1, 2, is equal to 0. This gives us an equation to solve in terms of lambda. So I get minus 3 plus lambda plus 1 plus lambda minus 10 plus 2 lambda is equal to 0. Mm, 4 lambda is equal to 0, so lambda is equal to 3. 2 lambda. I thought there was something not quite right here. Okay, so there's a 2 lambda, which we forgot to carry over. It's 2 lambda. So this would now be 4 lambda. So that gives us 6 lambda minus 12 is 0. Okay, lambda is equal to 2. Okay. So we want this vector AL. So now we can put lambda back in. So that gives us 1 or minus 1, 3 and minus 1. And then we want to work out the length of this vector. So we want the magnitude of this vector AL. And that's just going to be Pythagoras, which, yeah, is going to give us root 11. So 3 squared minus 1 all squared is equal to root 11. This kind of question is quite common. Again, looking for keywords like perpendicular, a dot b is 0. You can draw a diagram here as well to actually visualize exactly what distance that we're looking for. But key thing is you take the general form of it, you take away the specific point that we have here. So we have that particular vector that we're looking for. We want them to be perpendicular to the direction. So that means the dot product needs to be 0. Then we work out a value of lambda, so we actually have this particular vector, and then we find the distance of it. Okay, nice question. Again, this is 10A mark scheme here, and 10B. Again, we can take different methods here. We've generally looked at this method down here. Okay, and on to our last section here on the factor remainder theorem. If you've been liking this video so far, it's been a really good catch up of all things Pure 3, then do like and subscribe to the channel for more Pure 3 content. Right, so we have a cubic here, so 2x cubed plus ax squared plus minus 11x plus b, and we're given that this function is divisible by 2x minus 1. So what I quickly do here is I do 2x minus 1 is equal to 0, so x is a half. And what that means is that if I substitute a half into it, then I will get 0 out of the function. That's what's meant by divisible. And then if I put in x plus 1, so again, I quickly solve this and get x is minus 1. So what that means is if I put minus 1 into the function, I will get 12 out of it. And from that information, I should be able to work out a and b. Right, so let's start with f of a half. So if we put a half into this function, a half cubed is 1/8 times 2 is 2/8, which is a quarter. And then we have a half times a half is a quarter, that's also a quarter a, minus 11 over 2 plus b, and that's equal to 0. All right, let's tidy this up slightly. So This is the same as 22 over 4. To bring it to one side, that's going to give us 21 over 4. This is a quarter A plus B. Times it through by 4 just so we tidy it up slightly. So we get A plus 4B is 21 from that statement. And then we have f of minus 1 is equal to 12. So I put minus 1 into this function. Minus 1 all cubed is still minus 1 times 2 is minus 2. Minus 1 squared is positive 1, so that gives me plus A. Minus 11 times minus 1 is plus 11. Plus B is equal to 12. 11 minus 2 is 9. 12 minus 9 is 3. So that gives me this equation. Okay, this is pretty nice to solve. Again, we can just subtract one from the other. A minus A gives us nothing. 4B minus B is 3B. 21 minus 3 is 18. And therefore B is equal to 6. Now we just need to find A here. Again, we've got lots of choices of formulae. I think just using this one is pretty straightforward. So it has A plus 6 is equal to 3. Therefore A is equal to negative 3. These factor remainder theorem questions don't really change that much. Again, you're just putting in those particular values to either be divisible, i.e. equal to 0, or the remainder is equal to something. Again, gives you usually a simultaneous equation then to solve out of it. Fairly easy 5 marks for a pure 3 standard exam. So you can see the answers there. You could have also taken the other approach, which please do not do this approach, which is algebraic long division. Again, it just takes a lot of time to do. So if you've enjoyed this set of videos, again, please do like and subscribe. And if you want to get revision in on all things Stats 1, so that's paper 5, then do check out the video right in front of you, which will get you up to date with all things A-level Maths Stats 1, paper 5.